Hello and welcome again to construction planning and scheduling. And today we're going to talk about network compression or project acceleration. We're going to learn how to achieve more in less time through using more resources, and when to balance the extra cost that's going to result from these extra resources with the savings that might result from shortening that project duration. So the basic principle here is talking about the relationship between time and money. So far we have learned about cash flow management, but today we need to talk about, once we have developed a schedule, if the project, for example, is behind schedule and we have huge sums to be paid in liquidated damages, how to avoid paying these liquidated damages. This is going to be achieved through accelerating the project. Basically what we're saying here is that we're going to need to achieve more work in less time. Therefore, the duration equation was Q over P, quantity divided by production rate. The quantity is not going to change, therefore we need to increase the production rate. This is going to be achieved through, most likely, either changing the logic of the activities or using more resources for the activity, and these resources are going to cost money as per the definition of resources. So construction projects always have planned and expected finish deadlines assigned by the owner and stipulated in the contract. Whether the owner gives you 200 days, which are usually calendar days, to finish the project, or 300 calendar days or whatever, this is the time within which you have to finish that project. If the contractor cannot meet the deadlines, the contractor may need to pay the owner liquidated damages, which are assessed on each day, sometimes each hour, depending on the severity of the project, of delay beyond the planned duration. Depending on the conditions of contract, the contractor may receive bonus if he or she can finish the project before the deadline. So this would be called voluntary acceleration. The contractor wants to finish earlier than the set date so that they can move to another project and maybe get a bonus from the client. On the other hand, some contracts may also require or may also include a penalty clause above and beyond the liquidated damages clause for late completion of the project. As you may have learned in contracts and specs, liquidated damages are not a penalty. They are not considered a penalty, but they are damages that the owner would suffer from the late completion of the project. That's what the contractor would have to pay back. On the other hand, the owner may impose another penalty clause in the contract, which is usually counterbalanced by a bonus clause as well. So most likely, if the contract has a penalty clause, it's going to have also a bonus clause for finishing earlier than scheduled. So the liquidated damages are a stipulation in the contract of a monetary amount that must be paid by the contractor if he or she fails to satisfactorily complete the project by the contract finish date. A substantial completion is usually accepted to stop the calculations of liquidated damages, because by substantial completion the owner can practically start making use of the project. There are some still fine touches to be completed, maybe for landscaping or cleaning or something else, but the owner can have occupancy of the project and can start practically utilizing that project for financial benefit. A substantial completion is the date when the owner can practically start making use of the project, and is different from the actual completion where the contractor demobilizes from the site. So why do we accelerate the project? The contractor's normal finish date is the baseline schedule. In the baseline schedule does not meet the imposed finish date on the contract. So if I have calculated my schedule initially and I found that I'm going to finish in 205 calendar days, and the owner has given me only 200 calendar days, it means I have to shorten my project duration by 5 days. That's before even the project starts. After starting the project and during the project updating, a contractor may find that the project is behind the schedule. Therefore, if it's behind the schedule on critical activities, if we keep progressing at the same rate, we're going to finish the project behind schedule. We're going to be liable for liquidated damages. To avoid paying these liquidated damages, the contractor is going to initiate their own acceleration. The contractor wants to receive time incentives if so stated in the contract. So again, if there's a bonus clause in the contract that the contractor wants to make use of that bonus, then in this case they may voluntarily accelerate the project. Finishing the project early means contractor can move to other jobs. Again, if there are other opportunities that the contractor needs to use these resources for, then we're going to try to shorten the duration of this project in order to benefit from that new opportunity. It may be more profitable to do so. That's for the contractor. If, for example, we anticipate some material or equipment price increase in the future and we want to finish early so that to avoid this price increase, that would be another venue. The owner has directed the contractor to accelerate the project. In this case, it's going to be considered an owner-initiated acceleration, and usually the contractor would get some reimbursement for any extra costs that might incur due to that owner-initiated acceleration. How to accelerate the project? There are different ways. The first of which is to revisit or study the schedule thoroughly to find any errors or unnecessary logics or constraints. So, for example, if we have some activities that are done on a finish-to-start basis, what if we can do them on a start-to-start basis or with lag, or finish-to-start basic with overlap, so that we would shorten the duration of completion? Fast-track the project by breaking it down into smaller packages and starting the construction of earlier packages while the latter ones are still in design or bidding. This is what we call fast-tracking of the project. Conduct value engineering, productivity improvement, and constructability studies. Are we making the best use of our resources? Can we increase the productivity of that team of labor or of that piece of equipment or the coordination among these different resources? Change the method of construction or its sequence. Doing things in parallel rather than doing them in series one after the other might result in time shortening. Ultimately, improve the production rate, or P, in the duration calculation equation, Q over P. If I increase P, that means that while keeping the quantity the same, that means that the duration is going to drop. Other options, which is unfortunately what comes first to some people's mind, work overtime. Overtime might not always be the solution. Or offer incentives to workers or crews for improving productivity. Within the same time, if you can finish more work, you're going to get a bonus. Or acquire more workers and equipment, again, to work within the same time so that you don't have to work overtime. Because overtime, by the way, you know that you're going to pay a premium for the overtime, maybe 1.5 times the average rate, while you're not getting the same productivity. Because imagine if some worker have worked for 8 hours and you're asking them to work 3 more hours in overtime. You do not expect that their productivity is going to be the same as during the normal work hours. So you're paying more and getting less. Work a second or possibly a third shift. So you're going to have different shifts of labor, each one working only for 8 hours. And in this case, you're going to get fresh labor to work on the new shift. Acquire special materials and equipment that can help speed up the work process. For example, in concrete, we can have accelerators that are going to accelerate the setting up of the concrete so that we can remove the formwork faster. Therefore, we can proceed to the next floor faster. Improve project management or supervision. Again, project management and encouragement and so on. Proper supervision can provide better productivity rates. Improve communications among parties, particularly during the submittal process, to make sure that we get our submittals on time, we get our approvals on time, and we are not delayed by such paperwork. In order to accelerate the schedule, the contractor will most likely need additional resources or better utilize existing ones. As a project manager, you should know how and when to accelerate the schedule and understand the trade-off between time and cost. Because usually, as we agreed before, time is a resource. You pay money to acquire time. So what we're trying to do here is buying time by doing more in a shorter period of time, and that's going to cost us most likely some additional resources. For the time and cost trade-off, we're going to deal with some new terms, and basically we're going to deal with primarily 4 or 5 different new terms. Let's learn about them here right now. The original duration for each activity, which is also called the normal duration. Under normal conditions, how much would it take to finish that activity? And that's referred to as ND, or normal duration. The cost associated with completing the activity within its normal duration is called normal cost. So normal duration is the time it's going to take to do the activity under normal conditions, and the cost associated with that is normal cost. An activity may be shortened if it has compressibility, or the activity is called compressible, which means if I add more resources, these are going to result in shortening the duration of the activity. In this case, it's called a compressible activity. In some cases, you might find activities where whatever resources you add are not going to shorten the duration. In this case, it would be called an incompressible activity, and it would not be wise to add any resources to an incompressible activity. The shortest possible duration to complete the activity is called the crash duration. So if I used all the available extra resources to try to shorten the duration and resulted in compressing the duration of the activity to the maximum, this shortest duration is called the crash duration, or CD, which is achieved through the highest possible productivity and maximum, not necessarily optimum, use of resources. The cost associated with completing the activity within its crash duration is called the crash cost. So we have now crash duration, CD, and crash cost associated with it, which is CC, which is usually higher than the normal cost. So the crash duration, CD, is shorter than normal duration, but crash cost is higher than the normal cost. If shortening or compressing the original duration or normal duration is necessary, it should be expected that the direct cost of the activity is going to increase. Direct cost is the cost of these resources: labor, material, equipment, subcontractors, etc. The formalized method to handle this problem is called network compression, which is basically what we're learning about, or project acceleration, and this is also called time-cost trade-off, because basically you are trading additional cost for shortening the project time or duration. The objective of doing that is that the basic objective of network compression is to reduce the estimated project duration by reducing those critical activities in the CPM network. Of course, the critical activities are the ones that control the duration of the project, so it would not be wise at all to compress a non-critical activity. It's not going to achieve anything. You'd be wasting your money, which will result in the lowest added cost of the project. So we're trying to compress the critical activities, resulting in the lowest additional cost for the project. Some of the assumption: the original activity durations represent a method for performing the associated work at a low cost to the contractor, and the reduction of an activity's duration will require the expenditure of different or additional resources and will normally result in higher direct cost. Higher direct cost, which is the cost of the additional resources that you're going to need to utilize, again, labor, material, equipment, subcontractors. In order to identify the different costs and so on, let's get a brief introduction about what are the different types of costs and what are the different behaviors of these different types of costs. So the project costs can be classified according to different criteria, first of which is whether they are direct or indirect, and second, their behavior and relationship with time and other elements in the project. So according to the first classification, costs can be either direct costs or indirect costs. Direct costs are the costs directly related to the items of the project or are represented by a pay item in the bid. You may also say that these are the costs of things that the contractor intentionally leaves in the project on their way out. So the cost of bricks and blocks, the cost of concrete and steel, the cost of glass, the cost of carpet, the cost of electrical supplies, the cost of mechanical equipment that's going to be permanent in the project, like air handling units or things like that. All of these are going to be considered as direct costs, and you're going to have the examples of labor costs, material costs, and equipment that's going to be left in the project, or equipment that you rented to achieve something. So for example, if you have a tower crane or a loader or a bulldozer, you're not going to leave these in the project, but that their productivity is going to be left in the project. So if you rent this equipment for a period of time, their rental achieves certain direct objectives, whether it's excavation or laying concrete or whatever, and this is going to be part of the direct cost. The other type, according to this classification, is indirect costs, which are costs necessary for the completion of the project. You cannot do the project without these costs, but is not necessarily direct to any particular activity thereof. Examples of these costs include supervision costs, like the salary of the superintendent, who does not do any physical work but supervises all the work. Same thing for a security guard. Same thing for a project manager. The project manager himself or herself, since they do not do any physical work, their job is to manage the project. You cannot pinpoint any specific activity and say they did this on this activity or they did that on the other activity, but you're going to consider their salary and their expenses as indirect cost that is still needed for the project. That's one classification. Let's look at the other classification, which is the cost behavior with time. So we have under that classification, the first type is what we call the once-only cost. Once-only cost means that it's going to be spent only once in the lifetime of the project, either at the beginning or at the end, or somewhere in between. So for example, if we're going to have to pave a temporary access road to the site, to ease the access of the equipment and the materials to the construction site, this is a once-only cost. If you're going to have to build a fence, temporary fence around the site at the very beginning for security purposes, then this is a once-only cost. The installation of the trailers for the contractors and the subcontractors and the parking shed, all of that is going to be considered a once-only cost, because once you spend it at the very beginning, you're not going to spend it. Not going to spend any additional money on that until the project is over. Same thing can be done for the mobilization of the equipment at the beginning and the demobilization of the equipment at the end of the project on your way out. And as you can see, the behavior of that type of cost, on the horizontal axis we have time, on the vertical axis we have cost. There's a certain amount that's going to be spent at the beginning, and then it remains flat until the end of the project. The second type is, and these by the way are usually indirect costs. Most of the once-only costs are going to be considered as indirect costs, unless in very few on very few occasions you're going to have mobilization as a pay item in the bid. If the owner is going to reimburse you for mobilization, then that part is going to be considered a direct cost. The second type of cost is what we call time-related costs. So time-related costs means that these costs are going to be directly proportional to time, usually linearly. So as time increases, this cost is going to be accrued gradually and is going to increase. Example of this type include cost of rented equipment, if you use any rented equipment, and the cost of some types of labor, like administrative labor, administrative personnel, site and head office overheads. Any overheads are going to be considered as time related. So as we just defined, the salary of the project manager, for example, is time related, because regardless of the amount of achievement every month, the project manager is going to get their salary, and it depends on the duration of the project. So in general, most of the time related costs are going to be considered as indirect costs. Again, to tie the two classifications, the once only and the time related costs are going to be considered indirect costs, and the slope of this line is going to represent cost per unit of time. So cost per hour, cost per month, something of that sort. The third type of costs is going to be slightly different, because now on the horizontal axis we do not have time anymore, but we have quantity. On the vertical axis we still have cost. So now we're trying to chart the relationship between, or plot the relationship between quantity and cost. These are the costs that are directly proportional to quantity. As quantity increases, this cost also increases. However, the trend of the curve can take one of many shapes, including a straight line or a parabola, something like this. So examples of this type of cost include material costs, which is direct cost, subcontractors, which is direct cost, equipment operation cost, which is also direct cost. So most of these are direct costs. Now, we say that it might be a straight line, which is the cost per unit, so the cost per cubic yard of concrete, the cost per ton of steel, the cost per 1,000 bricks, and so on and so forth. It might be constant, or It might be a parabola like that, which shows that at the beginning we have a higher cost per unit and at the end we have a lower cost per unit. This is what we call the economy of scale, or buying in bulk. The more you buy, the more discount you're going to get on the price. So the larger the amount that you order, the lower the unit price that you're going to get, and that's why the unit price might not be linear. The question now is, if we want to calculate the total cost of the project, which is direct plus indirect, in this case it's going to be the once only plus the time related plus, which are indirect, plus the quantity proportional, which is direct. The dilemma that we have here is, how are we going to add these three costs together? The time related and the once only can be added together because they have the same units, time on the horizontal axis and costs on the vertical axis, so we can add these two graphs together. But we cannot add this third one because it has a different element on the horizontal axis, which is quantity. We cannot add apples and oranges, in this case time and quantity. Therefore we have to think about a way of converting this quantity cost curve into a time cost curve, and we can add it to the other two. Therefore we can get the total cost of the project graphically as well. So here we're going to start learning about something called the cost slope of activities. Now we're talking about direct costs only, cost of labor, material, equipment, subcontractors, etc. If you have this time, which is the normal duration to finish the activity, it's going to cost you that much, which is a normal cost. We agreed that if you try to shorten the time, you're going to need to use more resources. Therefore, if we want to do it at the crash duration, which is shorter than the normal duration, we're going to need to have a crash cost which is higher than the normal cost. So basically what we have on the horizontal axis here, the difference between the normal duration and the crash duration is going to be called delta T, or difference in time. That's the difference between normal duration and crash duration, which can also be referred to as the compressibility of the activity. This is the amount of time by which the activity can be compressed. And on the vertical axis, the difference between the crash cost and the normal cost is going to be the delta C, or difference in cost. So of course crash cost is going to be higher than normal cost. The slope connecting these two dots, the CC, CD with the ND and C, we're going to get what's called activity cost slope. Activity cost slope represents the average increase in cost by shortening the activity by 1 day. So delta C over delta T, how much is it going to cost on average for shortening the activity by 1 day? The units of the activity cost slope are going to be dollars per day or dollars per hour, depending on the units of that time on the horizontal axis. So talking about the activity utility curve, its essential data required for the application of network compression are the direct cost and time curves for the activity, and that's called the activity utility curves. So basically here, what we said, normal time and normal cost are going to give us a point. Crash time and crash cost are going to give us another point. This is going to be the relationship between the two, but for simplicity we're going to assume that it is a straight line connecting these two dots, as we have seen on the previous slide. Direct cost for each method of accomplishing an activity is plotted against the duration required to do it in that way. In practice, there are normally only a limited number of ways investigated, and thus only a finite number of points are defined. It's not an infinite number of methods, but it's a very discrete number of points. Basically, if I can finish it in 5 days, it's going to cost that much. If I finish it in 4 days, it's going to cost that much. If I finish it in 3 days, it's going to cost that much. So that's basically what we're talking about here. It's straight lines, short segments of straight lines, and we're going to approximate that by connecting these 2 points at the end to get the cost slope that we just talked about. That's pretty much the same thing. So this is the cost slope. S2 is the cost slope for moving from point 2 to point 3. Therefore, it's cost 3 minus cost 2, which is delta cost, minus divided by time 2 minus time 3, which is the delta time. The cost in the activity utility curve refers again to the direct cost, which is cost of labor, material, equipment, subcontractors, and other incidental costs that can be allocated to a particular activity. Some potential problems: it can take considerable effort to develop multiple point curves for all activities, therefore only important activities may be evaluated. You're going to learn that, or you're going to find out that in any project, only 20% of the activities of that project control 80% of the cost of the project. This is called the Pareto law. Pareto law, which is also known as the 80-20 or 20-80 theory. Basically, 20% of the activities of the project are going to cost 80% of the total cost of the project. So by being able to handle these 20% and draw these curves for these 20% of the activities, we are basically controlling 80% of the cost. It's assumed that an activity's duration can be shortened only one day at a time from one point to another on its curve. This may not be true, but usually does not pose serious problems in the final solution, so we're going to assume that this assumption is valid. A utility curve can also be developed for the total project from the compilation of the utility curves for different activities, or basically for the critical activities, because they are the ones that are going to be candidate for compression. So we can develop a utility curve for the whole project. The direct cost curve is developed by starting with the normal project duration and its associated sum of direct activity costs for that normal time, and then we add to that the indirect costs. The total cost is the sum of direct cost and indirect cost. So again, the indirect costs, as we have discussed it, include overheads, project staff, which are the management staff, office trailer, cars and trucks, office equipment, temporary utilities, etc. In addition to the general overheads from the head office, including main office expenses, rent or lease and maintenance and utilities, main office personnel, central legal department, central estimating department, central purchasing department, CEO of the company, and so on, all of these are considered as head office overheads for the project. So once we add the indirect cost, which is time related like this, to the direct cost, which is basically what we managed to convert the quantity proportional into a time related cost. So basically this is the direct cost at point 1, this is the direct cost at point 2, which is shorter duration, this is at point 3. So by adding these costs together, the total cost if we finish at point 1 is going to be that much. The total cost if we finish at point 2 is going to be that much. Total cost if we finish at point 3 is going to be that much. And if we finish at point 4 is going to be that much. So it shows that there is a certain point in the life of the project where it's going to be shortest possible, not shortest possible duration, but the optimum duration that's going to give us the shortest, the lowest possible cost. So the lowest possible cost is going to be achieved at point 2, which is not the shortest duration. Shortest duration is point 4. It's not the longest duration either, which is point 1, but it's somewhere in between. So for example, in an earth moving project with a productivity of 160 cubic yards per hour, total work is 16,000 cubic yards. Equipment operating cost, except for operators, $50 per hour. Operator wage and benefits, $32 per hour. All of this is under normal conditions. Then if you need to shorten, then the overtime wage and benefits is almost 1.5, $48 per hour, and indirect cost per day is $100 per day. Draw the project utility curve. So first of all, we have to establish the normal duration, which is 16,000 cubic yards divided by 160 cubic yards per hour. That gives 100 hours. So once we know that it's going to be finished in 100 hours, we can calculate the cost of labor during these 100 hours as well, which is going to be the $54 per hour plus the $32 per hour. All of this is going to be the direct cost for the project. Now, if we want to shorten that duration from 100 hours to shorter than that, then we're going to use overheads. The more overhead hours, the shorter the duration of the project, but the higher cost by adding these overtime wages and benefits. And then you can calculate the net, because each day that you shorten, assuming that we're working 8 hours a day, so 12 and a half days, each day that you shorten, you're going to save on the indirect costs $100 per day. So you're going to pay more in the direct costs, but you're going to pay less in the indirect costs, and that's going to be the balance that we're going to be looking for. The objective is to shorten the total project duration by compressing the duration of activities on the critical path. Only critical activities will be considered for compression. Remember now that we're going to have 4 conditions, so you have to remember these 4 conditions before you can start compressing, before even considering an activity for compression. These 4 conditions are, first of all, the activity has to be critical. If it is not critical, do not consider it for compression. Number 2, it has to be compressible. If its delta T is equal to 0, which means its normal duration is the same as the crash duration, then this activity cannot be compressed, so do not waste your time or money. Third, it has to be an effective activity. And this is the very interesting part here. If you have 2 critical activities that are connected by a start-to-start relationship, if you compress the duration of the first one, is that going to affect the completion date for the second one? The answer is no, because they are linked by start to start. So the completion of the first one does not affect the shortening the duration of the project. Same thing if you have 2 critical activities connected by a finish-to-finish relationship. What's driving the completion date for the second one is the relationship with the previous predecessor. So if you shorten the duration of that last activity by itself, it's not going to achieve anything, because it has to wait for that number coming from its predecessor anyway. Therefore, if you have a start-to-start relationship on 2 critical activities, the first one would be considered ineffective. If you have a finish-to-finish relationship on 2 critical activities, the second one or the successor would be considered ineffective. Once an activity satisfies all of these 3 conditions, it's critical, it's compressible, and it's effective, we have multiple activities satisfying all of these 3 conditions, then which one to start with? The cheapest one to compress, which means the one that has lowest cost slope. So among the critical, compressible, and effective activities, we will start with the activity or activities with the lowest cost slope, then move to other activities in an ascending order of their cost slope. So I'm going to keep the most expensive activity until the end. So the basic procedure is start with the critical activity having the flattest or the lowest cost slope, and then considering successively those having steeper or higher cost slopes. If non-critical activities, now while we are compressing, we're going to keep an eye on the non-critical activities. The non-critical activities are recognized by having total float. But each time we are compressing the duration of the project, that total float decreases until a certain point in time where the activity might lose all of its total float, the non-critical activity might lose all of its total float, becoming activity, then it becomes a new candidate for compression. If non-critical activities lose their float time and become critical duration the compression of the original critical activities, then these new critical activities must also be considered when selecting activities to compress to further reduce the total project duration. Question now here is, I started with one critical path and several other non-critical paths. While doing my compression, one of the non-critical paths became critical, so now I have 2 critical paths. Which one should I compress to reduce the total duration of the project? The answer is both. Because if you compress one and leave the other, if you remember the definition of the critical path, it was the longest path in the network. So if you compress one of them and leave the other one, then that one that was left without compression is still going to be the longest path or the critical path, and we have not achieved anything. So if you're going to compress two paths, you have to compress both by the same amount at the same time. So the safest method is going to be compress the network one day at a time, unless the minimum total float on the non-critical activities is greater than 1 day. So let's say the minimum total float on the non-critical activities is 12 days. It means that I can compress the network, the original critical path, by up to 12 days before creating a new critical path. Once I recognize this fact, I can compress more than one activity by more than 1 day in one single step to simplify my calculations. At each stage of the network compression calculations, we're going to follow these steps. First of all, identify the critical activities. Second, delete from considerations those with zero potential for compression. If they have delta T equal to 0 or they are incompressible, then we're not going to look at them. Among the critical activities, exclude the non-effective ones. As we said, the predecessors in start-to-start relationship and the successors in a finish-to-finish relationship. Number 4, select that activity or group of activities if parallel critical paths exist with the lowest combined cost slope, if you're trying to compress more than one path at the same time. And always watch for the creation of new critical paths, so keep an eye on the total float of the non-critical activities and watch if it's dropping and these activities are becoming critical. At each stage of the network compression, we're also going to notice compress the activity or activities as identified in step 3, update the network time calculations and the corresponding project direct cost. Repeat these steps until further reduction in the project duration is not possible, or until the desired project duration is reached. So for example, we may say, I do not want to compress the network to the maximum, I just need to save 3 days, so I'm going to compress it only by 3 days and then stop. The project is late by 3 days, I don't want to shorten it beyond that, so only 3 days of compression are going to be needed. Or until the cost of compression is no longer economically feasible or meaningful. So if the question is, compress the project duration until I reach that lowest point on the total cost curve. Beyond that, compressing the duration is going to result in another increase in cost. I don't want that. So I just want to reach the lowest cost point, which is going to be called my optimum duration. So we're going to stop here for this time, and then in our next lecture we're going to look at an example and we're going to solve that example in systematic steps. I'll see you in a short while working on that example.